We're going to be presenting some of the work of the UVM. Hello, and welcome to this tutorial on the Accellera UVM AMS standard. I'm Tom Fitzpatrick from Siemens EDA. I'm also the chair of the UVM AMS working group. And today, with my colleague Tim Pylan of Cadence Design Systems, we're going to be presenting some of the work of the UVM AMS working group and sharing with you kind of where we're at with the standard. At the end of the presentation, some additional colleagues from the working group will be available to answer any questions that come up during the presentation. So let's go ahead and get started. So why are we doing this? Well, with this data from the International Business Strategies, we can see that 85% of design starts are mixed signal in nature. So this includes several different industries, including 5G, automotive, IoT, and others. And this is leading to more and more recognition of the risks and challenges in mixed signal verification. Right, so just like we did 10 years ago with UVM for digital verification, teams are now beginning to realize that AMS verification is going to require more advanced methodologies for modular, scalable, reusable, coverage-driven mixed signal verification. So kind of all the reasons that things like UVM were created initially for digital verification, we now recognize that we need the same kinds of things for analog and mixed signal verification as well. So the working group was formed, and we have a number of companies, both vendors and users, that are participating in the UVM AMS working group in Accellera. And we're always looking for more members, by the way. So if you happen to belong to a company that is an Accellera member, you're more than welcome to join us in the committee. If you're not an Accellera member and would like to become one, we can certainly help you with that as well. And if you work for any one of these companies, feel free to reach out to your local rep. And if you want to participate in the working group, we'd love to have you. Before we get too far into things, I do want to take a moment here to make sure that we all agree on the terms we'll be using. So when we talk about AMS simulation and verification, this refers to systems that can simulate and verify AMS designs. We can do that either through co-simulation, where we have a digital engine combined with an analog or electrical solver, or we can do that with an event-driven digital engine that can include analog real number models. This is sometimes referred to as digital mixed signal verification. And also, so we're talking about the same thing. When we talk about UVM, we're talking about the IEEE 1800.2 standard verification methodology. And the idea of UVM is that it provides modular, scalable, reusable, and interoperable verification IP, stimulus, test bench components, and environments. This is currently in use by over 80% of ASIC verification teams today and 50% of FPGA verification teams, so it makes sense that we'd use this as our target methodology. So when we combine these ideas of co-simulation, both analog and digital mixed signal simulation, with UVM, we get UVM AMS, which is a comprehensive, unified analog mixed signal verification methodology that will improve both AMS and DMS verification of integrated circuits by bringing these concepts of modularity, scalability, and reusability to allow us to create the same similar kinds of verification IP, stimulus, and test bench components to an environment required to verify an AMS design. So what we want to do here is we want to start with UVM, which is a class-based library in System Verilog for digital verification, and we want to extend as necessary that class-based approach for UVM and possibly create an accompanying set of additional components and or packages in System Verilog or Verilog AMS to be able to produce stimulus, tests, sequences, components, and analysis functions for AMS and digital mixed signal designs and verification. So we want to be able to improve those in the same way that the use of a methodology like UVM has improved digital verification over the last decade. So we want to define a framework that will allow us to create analog and mixed signal verification components and test benches by introducing extensions to the idea of verification IP from the digital-centric world of UVM. We're going to base it on existing standards. And we also will then promote the use of the UVM AMS standard among the verification community. And that's where we're going to need your help to do that as we move forward. So before we can build on UVM, we need to know what it is we're talking about when we talk about UVM. So just a very quick overview of UVM here. So if we start with our DUT, we need to be able to communicate to the DUT, and the way we communicate with the DUT is by definition protocol specific, right? We have some protocol that we're going to use to communicate to the DUT. In UVM, we have a UVM agent, or sometimes called a UVC or a UVM verification component, that is protocol specific, that includes everything you need to do to communicate to the DUT given the certain protocol. Now, the way we actually connect from the class-based world of UVM and System Verilog to the module-based world of the DUT is through this thing called a System Verilog interface. A System Verilog interface is essentially a group of signals. It can also include methods that you might call or whatever, but it's basically a group of signals that connect to the DUT. And in the class-based side of things, we have what's called a virtual interface, which is essentially a pointer to the interface that's connected to the DUT. So we have regular components in a UVM agent called a sequencer, a driver, and a monitor, and we'll see what those do in a minute. Then, depending on what the design is required to do, there might be multiple UVM agents to talk to the different interfaces of the DUT, or other things like coverage that we're going to want to be able to measure about the DUT. These are design specific. So the UVM environment is the test bench that is specific to the design, whatever that might be, however many interfaces there are or what have you. And the sequencer's job is to generate transactions that go over to the driver. The driver takes the information in that transaction, what we call a sequence item, and it will convert that into pin level activity on the interface. Right? So the transaction or the sequence item may define things like address, data, number of delay cycles, whatever it is, and then the driver will cause the protocol specific behaviors to happen on the bus to make the communication to the DUT happen. The monitor is sort of the reverse of that. The monitor sees the pin level activity on the interface and extracts the information from that to create another sequence item that may be the same information that was sent by the driver, or it may be additional information, including like the response from the DUT, if it was a read transaction or something like that, right? So the monitor collects the information from the pin level activity on the interface and turns it into a transaction that can be used to record coverage or send to a scoreboard or what have you. So the monitor is there to take that information and send it out to whoever needs to use it. And the environment will define what those connections are from that monitor to a coverage collector or a scoreboard or whatever. And the other thing the environment does is it configures the agent depending on what it is that we need to do. So you might have an active agent that has a sequencer and a driver and a monitor, so it's going to send transactions to the DUT and record what's going on. When you move up a level, that interface may now be driven by some other piece of the design in a subsystem or what have you, in which case you may want to set up your agent to be passive, so it won't have the sequencer and the driver, but it'll still have the monitor. So that's some of the configuration information that gets communicated to the agent based on what it is you need to do to the design. The test's job is to define the scenarios that we're going to execute on the environment through the agents talking to the DUT. So the test is going to essentially just define a few little things that are going to be used to tell the environment what to do. One of the most important things to tell the environment what to do is what sequences to run. So what are the sets of transactions that we're going to generate to the driver to make the stuff happen on the DUT. Right? And this is where the constrained random comes in. What are the values of the parameters in the sequence items that the driver is going to use to create the bus level activity? And if we have multiple agents, how are we going to coordinate the activity across the multiple agents through the sequences that get run as defined by the test? The other thing that the test can do is modify elements in the environment or the agent using, in what we call in UVM, the factory, right? This is a standard object-oriented programming pattern that allows us to change the type of component in the lower level elements of the test bench without having to change the code of them, right? So the UVM agent, when it creates the driver in the first place, it asks the factory for a driver. The test says, when the agent asks for a driver, give it the blue one instead of the gray one. Right? So as long as the blue driver is an extension of the gray driver, the base type, we can do that. And we can do similar things for the monitor, the coverage collector, the scoreboard, what have you, right? So the test can use the factory, it can define a set of sequences, it can also configure the environment to do certain things. And that is how we tweak the test bench to be scenario specific for the particular test that we want to run. So what is probably going to happen is you'll have an environment that is design specific, and you'll use that environment in a variety of tests where each test has a different set of sequences, factory override commands, configuration, or what have you, to make the same environment create different scenarios for the same DUT to verify different requirements that you have in your verification plan. So once we put all of this together, we now have to think about, what do we do if the device under test is analog, right? Because all of what we've done here is focused on the idea of these transaction items being generated by sequences. The driver uses them to initiate behavior on the interface. How are we going to do that with analog behaviors? And so what we need to do is to understand how we can extend the idea of a driver and a monitor from the digital realm, and also a transaction item that defines what is the information that needs to be communicated across that protocol, and use that for analog devices as well. So basically what we want to do is to define these analog behaviors that will be based on the set of parameters defined in the sequence item, and generate that analog signal in some way. And we're going to use what we're going to refer to as an analog resource or an MS bridge. So you'll hear Tim using that term quite a lot, actually. We also want to be able to measure the properties of that analog signal and return them to the monitor, and then package those properties into a sequence item that we can then use to record as coverage or send to a scoreboard or whatever we might need to do. We also want to be able to drive and monitor different configurations that are going to be controlled by dedicated sequence items that'll support easy integration into multi-channel test sequences. So we may have multiple signal generators in the same way that you might have multiple agents talking to a device through different interfaces. At the same time, we might want to be able to do the same thing in the analog sense, where we want to set up different signal generators and have those things be combined in interesting ways. So this will allow us then to define these controls and set them using constraints for pre-run configuration. So we can rely on the System Verilog constraint solver to choose the values that will then be applied to our analog test bench to make these different interesting configurations happen. And then we also want to be able to collect and check the coverage based on these property values from the analog resource as measured, or potentially add additional checkers in the analog resource, some way of measuring what's going on and turn that back into information that we can use in coverage collectors, scoreboards, or what have you, back up in the class-based environment. Now, when it comes to generating and driving these kinds of analog signals, we do have to be a little bit realistic. So if we think about an analog signal that is interesting, it needs to be a periodic waveform like a sine wave or a sawtooth or some other composition of such things. And when you think about those kinds of signals, there's specific information you need in order to be able to have it do certain things. So you need the frequency, the phase, the amplitude, and the DC bias. And with those four things, you can generate a wide variety of different sine waves, as an example. Given that, we can make those four things, frequency, phase, amplitude, and DC bias, elements of a sequence item that we will use to control the signal generator in the analog realm, but generate the values from the UVM sequence. Right? So the sequence item is going to contain the fields for the control parameters to tell the analog generators what to do. And the driver is going to convert that transaction or that sequence item into setting the information to the signal generator. So in the same way that a regular UVM driver takes the information in a sequence item and generates the pin level behavior to communicate with an analog DUT, in UVM AMS, we're going to have a sequence item that's going to contain fields to control the analog behavior, whatever that's going to be, and send that through a driver where the driver will then communicate to the analog generator to do the right thing. So in the same way that we have for UVM AMS will rely on these sequence items to provide a relatively simple control interface for the test writer that's going to make it easy to control the generated signals on the fly. So if we have this ability to define a set of sequence items through a driver to control analog signal generators, we can then combine multiple signal generators to achieve more complex input signals. So whether we're talking about modulation or noise injection, we can take these multiple signal generators, each one of which will be controlled by a transaction or a sequence item generated by the sequence through a driver that will control the different generators. And from that, we can create these interesting kinds of signals. Now, if you want to take it to the extreme, back when I was taking my early digital signal processing classes back in college, a square wave, also known as a set to 1, wait a little bit, set to 0, wait a little bit, and set back to 1, can be modeled as an infinite series of harmonic sine waves. Now, obviously, we're not going to do that, because if all we want is a square wave, we have much easier ways of doing that. But you can picture the same sort of thing, right? So you can have any kind of signal source that you need, and all you have to do is think about what information do I need to communicate to that signal generator to create the kind of analog behavior that I need to have to verify my design. Think about that, take a step back up to the sequence level, generate that transaction, and rely on the modularity of UVM to say, okay, I'm going to send that to my driver, and the driver will communicate to the signal generator. And most importantly, I don't care at the sequence level what that signal generator actually is or what it does. All I need to know is what information do I need to give it to have it do the right thing. So I don't care whether it's actually a SPICE model or a real number model in a DMS verification or whatever, right? There's the idea of abstracting that information allows us to create the test at a high enough level to say, okay, I want to generate a sine wave of this frequency starting now, and then do some other stuff. And when I get some other signal back in, maybe if I get some particular transaction on the bus, I say, oh, okay, now I want to double the frequency of the analog signal or whatever, right? So I can recognize that and then send another transaction to tell the signal generator to change. exactly the same thing as in UVM, saying I want to write to this memory location, and then when I read from this and get some other value, I want to go do something else. Right? So the idea of using what in UVM is a regular set of interfaces to define the sequence items to the driver, and hide the information, right? When I say I want to do a write to a particular address, I don't care in the digital realm whether I'm going to PCI or AHB or whatever. I don't care about what the protocol is. That's information that is built into the driver. The driver is going to take the information out of the sequence item and use the appropriate protocol. For analog signals, we're going to do the same thing. The driver is going to take the information out of the sequence item and then make the appropriate stuff happen to create the appropriate signal that we need. So with that as background, now we sort of know where we're trying to get to. I'm going to now hand it off to Tim and allow him to tell you how we're going to actually get there. Tim?
Thanks, Tom. So let's look at those challenges that Tom mentioned with driving mixed signals from a UVC, mainly the ability to drive a continuously changing signal. So here we have the standard UVC with the driver monitor connecting through the interface to the DUT. And with the standard UVC, the driver will set the value of a signal in the interface, and then that will trigger an event to occur on the DUT. But on a continuously changing signal, you're not specifying the value of the signal, you're specifying the characteristics of that signal. So they aren't really signals that you're controlling through the interface, they're attributes. And so in order to handle that and to produce a signal from those attributes, we're proposing the introduction of a MS bridge to be added to the UVC. So this MS bridge is a system Verilog module that sits between the UVC and the DUT, and it consists of a proxy that allows you to use functions in the proxy to pass values from the driver to the bridge that can then control the generation of signals. It still consists of the interface that connects up to the UVC. So if there are signals, discrete signals that are driven from the UVC, those will still be communicated in the same way through the interface. And then there's an analog resource. And this analog resource will take the values from the proxy and generate a signal that's passed to the DUT. It will also take any signals driven through the interface and also pass those through to the DUT as well. So this analog resource can consist of passive components like capacitors, resistors, inductors, etc. It can be voltage sources or even our continuously changing signal like our sine wave. It can be written in system Verilog, or if you need it to drive electrical signals in the analog domain, it can be a Verilog AMS module. And that's why you need to have all the signals from the UVC to the DUT being driven from the analog resource. This is so that you can change the analog resource from a system Verilog model to a Verilog AMS depending on whether the signals on the DUT are electrical or logic or a real number net type. So by having all of those signals driven from the analog resource, it's very easy to change the representation of that depending on what you're driving in the DUT without having to modify the bridge or the UVC. So the proxy, again, is an API back to the UVC, driver and monitor. So the driver and monitor can communicate with the bridge and therefore the analog resource through this proxy that's a class handle that can be passed just like you can with a virtual interface. And so it's going to be a system Verilog class that has functions that allow you to communicate with the analog resource. So here's an example. First of all, you have to create a proxy template, and this is just a virtual class that has the pure virtual functions in it, which is just the header information. It doesn't have any of the actual functionality implemented yet in this, but you need this proxy template so that you can include it into your UVC and make those functions available to the driver and monitor. And then inside the PGA bridge, you'll create a class that extends from that template class and fills out the implementation of the function. In this case, the config wave will have the amplitude, bias, phase, and frequency passed to it from the driver, and then those values will then be passed into the core, as we'll see more detail in the next slide. And then finally, use a config DB just like you would for your virtual interface to define the path to that proxy in the bridge, and then that path can be used within the driver and monitor to access the functions down inside the bridge. So here's the full implementation. We have our class proxy that defines our two functions, config wave and get measures. And here the driver will call config wave to pass in the amplitude, bias, phase, and frequency. And then those values will then be passed into the core, or our analog resource. And then once inside the core, those will then be passed down. In this case, this is a Verilog AMS module that has some analog code, and so those values will be used to generate an analog sine wave that can then be driven out onto electrical ports. We can also have pull functions. This would probably be used inside the monitor to get values out of the eventually the DUT, but in this case it's getting them from the core. And so here the get measures will be called. The values from the core, the amplitude out, bias out, phase out, frequency out, will be read and put into the corresponding variables that will be passed back through the get measures function into the monitor. And so you can read values out of the core, which is connected to the DUT. Or you can have monitored values, in which case whenever a signal down inside the core gets updated, that value will then be passed into the MS bridge, which will then be passed into the proxy via the assign statement. And so this will just trigger anytime a value is updated inside the core. Anything watching that on the UVC side will see the update and will trigger. So let's look at how this is implemented for our example design. Our design is a programmable gain amplifier. So we have two analog inputs, our INP and INN, and these signals are sine waves in this case. And then our output is the input signal multiplied by some specific gain dependent on the VCVGA programming. That's a 3-bit value to specify how much gain is applied to the input to drive out onto the output. So here's a port list for that DUT. We have our logic signals for our VCVGA, and our power down control. And then we have real nets, which are just system Verilog net types that have been defined to have a real number on the net. And we have real nets for all of our inputs and outputs that are going to be analog signals. So let's look at the simplest case where those values that we're driving don't need to be generated. They're just going to be static values that are going to just be passed to our gain amplifier. In that case, we don't have to use a proxy. We can just set the real values, real analogic values, pass them through the interface, and then the analog resource just takes those values and passes them to the corresponding ports on the DUT. And we can do this because it's just a static value that's passed and nothing has to be generated within the analog resource. And then if we do swap out the DUT with a SPICE model or something where there's electrical ports, like in this case where the outputs and the inputs are now electrical signals. We still have our logics for the power down and our VCVGA. Those are still input wires, but everything else is going to be electrical. So in that case, we can still drive the signal values through the interface because they're still just static type signals, but we need to convert them to something that's compatible with the electrical domain. So in this case, you would need to use a connect module, which is a Verilog AMS construct that supports both Verilog and analog within there. So you can access the Verilog side to get the values that are being passed from the interface, and then you can assign that to a voltage and current to drive the electrical signals on the output ports or on the ports that are connected to the DUT. And so you can see here the significance of having the analog resource even when you're driving just regular signals. You want the capability of being able to swap that analog resource easily depending on what types of ports you're driving without having to change anything in the MS bridge or the UVC. And so in this case, we just use a tick define or a config statement that brings in the Verilog AMS version of the analog resource instead of a system Verilog version. And we can do the same thing for if the signals are logics or reals. So if it's a sine wave, you need to have the proxy. And I'm sorry, on the logic to electrical, if it's a logic to electrical, you do need to have a proxy in this case. I missed that point that you need to program the analog resource to know what the supplies are, because a logic 1 needs to associate with the actual value of the supply on the electrical side. So you'd use a proxy to specify what the supply is, and then now when a logic 1 is detected, it can drive the supply voltage on that electrical. And then you'd also need a proxy if you're driving a continuously changing signal like a sine wave. So in this case, we'd use our proxy to pass in the values of our frequency, bias, etc. to generate that signal, and then we'd still use the interface to pass in the VCVGA and PD because those are logic signals. So you can see how the proxy and the interface can work together with the analog resource to generate those analog values for the mixed signal design. The other thing that we want to take out of UVM is the ability of messaging. UVM has a very powerful messaging capability built into it that can report errors, debug messages, and can also respond to those actions. So if you get an error, you can specify what the action is. Does the simulator stop? Does it just report the error? Does it totally end the simulation? So you can put specific actions on those messages, as well as specify the format of the message. And there's also counting counters built in, so you know how many warnings for each type of error you get, etc. And these can all be extracted out and used for generating your regression reports at the end. So as I said, these are macros that are built into the UVM library. And so you have your info message, which just displays a message based on a verbosity filter. So the nice thing about the info messages is you can put different levels of verbosity. So if you're just running a regression and you don't want a lot of messages, you can set a high verbosity, versus if you're in a debug and you want a lot of messages so you can debug, you can change the verbosity filter to be very low, so you get all those messages being printed out. And that's built into the UVM info. Then you also have the UVM warning, errors, and fatals that have associated actions and counters built into those. So the issue is that they are system Verilog macros. And of course, in our analog resource, there's likely that analog resource is likely going to be a Verilog AMS module, which means it can't use the system Verilog macros. So how do you take advantage of a system Verilog macro? And we're going to use the upscoping capability that's in Verilog and system Verilog since the 1364-2001 LRM. And that is and that Verilog syntax is supported in Verilog AMS. And so we can use this upscoping within our Verilog AMS to access the methods in our bridge by using the upscope capability. So in order to do that, we need to include a few extra parameters and functions. So inside of the Verilog AMS file, we want to include this UVM AMS include file. You can name it whatever you want, of course, but the key thing is that there's going to be local params specified in there to set up our strings that we're going to want to print out. And then we're going to create this UVM AMS include file that's going to have functions that correspond to those UVM info, warning, error, fatal macros that are in the UVM library. And so now within the Verilog AMS file, you can call UVM info function that will upscope, find that function inside the bridge, and then the bridge will pass the values into the UVM corresponding UVM macro. So let's look at how that works. So here's our parameters that we want to set. We have a parameter string for our UVM path, which just returns back the path to the analog resource. And then we'll have a local param message that specifies a message that's in the same format as what we would pass to our tick UVM info in the UVM world. And then inside of our analog resource, when we want to print a message, we just call UVM_info, set up our tag, pass in pass the message, the verbosity, and the UVM path parameters. So you notice that it's the UVM info function and not the macro. So it will use upscoping to look into the bridge. In the bridge, it will find that UVM info function. All the arguments get passed into it from the analog resource, and then those get passed into the actual UVM macro, in this case tick UVM info context, where we can pass in the ID message, verbosity, and the path. So this is the workaround that is being proposed in order to take advantage of the UVM messaging within the analog resource, which can be a Verilog AMS file. So let's wrap this up with a few facts. One of the questions is, what's the value that UVM AMS standard brings to the community? And this is very simple. The value is that we can take advantage of all the work and IPs and standards that have been created around UVM, and now apply those to mixed signal designs where you have analog ports, whether they're real number ports or electrical ports, and you can still take advantage of all the standardization and IPs that have been built around UVM. The next question, if I use a interface verification IP, so this is an IP that drives a specific protocol. It only supports digital signals. Should I replace them with AMS verification IP? So the answer to that one is that the UVM AMS standard makes that possible, where you can take existing digital VIP and either update it or add analog signals. So if the standard has been updated and is now allowing the use of analog signals on the ports of that IP, then UVM AMS standard will allow you to just pull the old digital VIP and put in the new mixed signal VIP, and it will drive the same ports with just different representations. But the important thing is you can still take advantage of all your UVM test bench code, all your sequences that generate the data. All of that UVC data is still valid. All your test bench data is still valid, because all we're doing is adding in the MS bridge that allows the use of a proxy if a proxy is needed, or passes the signals through the analog resource to the corresponding ports, and allowing the use of analog ports if that is needed. So that's the whole purpose of UVM AMS, is to make a very easy transition from a digital VIP to a mixed signal VIP, and still staying in the UVM context. Is the UVM AMS working group going to develop specific VIP? The simple answer to that is no, we're not going to develop VIP. The goal is to establish the standards so that those third-party vendors can develop VIPs based on the standard that will work just like in UVM, except with the capability of having the proxy to program analog signals and the ability to have an analog resource that can drive analog ports as well. That stated, we have generated some examples and are posting those to our UVM AMS working group GitHub site, so those examples will be available for you to use for training or take and modify and use for your own examples. In conclusion, UVM has been great, but it has that one limitation of working with mixed signal designs. And so this proposal addresses those gaps and provides the capabilities to generate analog signals, continuously changing signals, taking advantage of messaging within Verilog AMS, and all that while still maintaining the standard of working with standard UVCs with the sequence driver and monitor, and all the messaging that you have built into that. So with that, let's open it up for questions. Thank you.
All right, thanks, Tim. So Tim, are you online? You turn your camera on, please.
I am.
Hey, great. All right. All right. So you have Tim and myself here. There was a fairly interesting discussion going on between Dave and Jonathan about whether or not we should be using interface classes as part of this. We'll take that discussion offline, I think. There was one question from Scott. Will this work with the UNL netlister? I don't know what that is. Do you know?
So UNL netlister, so it will produce a Verilog AMS netlist, and you can, you should be able to use that. I'm trying to think, there will probably be some modification. Well, no, it should be used as is, or with minor modifications. You should be able to use a UNL netlist.
Okay.
It's just a Verilog AMS block, so it should drop right into the resource.
In a basic system Verilog, plus some AMS and UVM environment without, UVM AMS itself, I would instantiate the interface inside a system Verilog module that would pull the real number up and then connect that to some other module that could be either AMS or Verilog.
Right. That's the MS bridge. The MS bridge is just the MS bridge is a system Verilog module that has the interface instantiated, as well as the core, which could be either system Verilog or Verilog AMS. And the interface would connect up to that analog resource.
Okay, I was always calling that a translator for the last few years.
Well, now you'll call it an MS bridge, Jonathan. So.
Yeah, they're calling it an MS bridge. I was always calling it a translator because the agent goes into a foreign land, and
right.
that was my terminology for it. But anyway,
so it may or may not. The translation is only required if it's a Verilog AMS code for your analog resource. But if it's system Verilog,
actually, I use that same pattern when I'm controlling, something. I have in my digital mixed signal, I have stuff that's not standard system Verilog. I mean, not standard UVM stuff. So I do a lot of real numbers, even in my standard stuff. And I can't, because of PLI communication, I can't pull that into the actual top level module. So I actually still use that same pattern in my DMS environment.
Okay. All right, we got a question from Chuck. Will the SV-AMS standard help alleviate some of the system Verilog to Verilog AMS discrepancies, such as the UVM messaging stuff or construction of the MS bridge? So the answer to that is yes, that's part of why we're doing this. So UVM has all of the messaging infrastructure and everything else involved. All we're doing basically is extending that capability to make it easier to connect your UVM environment to an AMS design. So that's where the MS bridge comes in, but all the rest of it, you'll still have a UVM driver, you'll still have a UVM monitor, you'll still have access to all the UVM messaging stuff. So then he said, does the MS bridge code handle UPF to and from electrical ports?
I think that might be vendor specific, and possibly. the UPF would primarily be associated with the DUT, and so but But there are vendors that support driving UPF with.
Yeah, so we're not dealing with UPF at all in the standard, in the UVM AMS standard. So right, there are limits to what you can and can't do in any particular standard. So we are defined as extending the existing UVM system Verilog implementation to allow for connecting to AMS. Within that context, if there are certain things that we need to do, like we're looking at possibly making some proposals to system Verilog 1800, which is currently in a modification stage as well. So we might look at some minor extensions to system Verilog to support the kinds of things we need to do here. That's still a little bit up in the air. All right, a question from Saurabh. How seamless is the MS bridge connection, or how seamless would the MS bridge connection be to the homegrown signal types for analog, like ones created using PLI functions? So MS bridge connections to homegrown signal types for analog, like ones created using PLI functions. To the extent that an MS bridge is just a system Verilog module and the analog resource handles the conversion of types, I don't see that there's any reason we wouldn't be able to do that, right, Tim?
I'll go with that without getting more information about what he's.
Yeah. Okay. Right. Again, the thing we're only using standard system Verilog and existing Verilog or system Verilog AMS as the basis for the standard. So if you're doing something on your own that goes beyond those, to the extent that what you're doing is an extension of an existing standard, you would be able to do the same thing using a UVM AMS, but it's not going to be anything we build in the standard. We just couldn't do that, but we should give you the platform that you'd be able to use to extend in the same way that you're extending system Verilog or system Verilog AMS today. So, all right, let's see. Is the system Verilog AMS standard providing new features to help collecting functional coverage from analog?
Jonathan David has an answer right below it.
Oh, put its types in the submodule in the bridge.
Mine was the answer to Saurabh's question.
Oh, okay.
Yeah. Okay.
Oh, put the PLI on a submodule.
Yeah, with the PLI thing.
Yeah. Okay. All right. As far as she's question, so again, we're talking about the UVM AMS standard. There is an existing system Verilog AMS standard that there's not a whole lot being done to it at the moment. So we are not adding new features to system Verilog AMS. To the extent that UVM supports functional coverage, and what we're talking about is defining sequence items that include information that can be used to tell the analog stuff what to do, or if you can record what's going on in the analog stuff and turn that back through the UVM monitor into another sequence item, you can cover that. So if you had, let's say, a variable frequency sine wave generator in your analog, and you wanted to cover that, you checked all these different frequencies of it, as long as you can measure the frequency of the sine wave and get that information back in the UVM, you could use that as just another regular UVM coverage parameter, right? All right. Let's see. One more question. Is the UVM AMS doing anything for reference models of the AMS system? No.
Yeah, that was one of the questions. We provide some examples, but we're not providing any kind of library or anything.
Yeah. This was more specifically for
if you have a reference
standard
model,
UVM, right? For standard UVM, in the scoreboards, there is usually some sort of a reference model thing going on to collect the information. Sure. Is there any effort to do something like that for analog subsystems within the UVM, to extend the TLM stuff in a way that will help analog more?
Not to extent, but I have used scoreboards with reference models with this configuration. And the reference model just reproduces what the DUT would do with the same information.
Yeah, so if you have a reference model in C or something, you can include that in your UVM environment the same way you would if it were an RTL reference model or C model. Right? Does that make sense, Jonathan?
Yeah, this has been my focus for some time, so
Okay.
I have some ideas here, but I don't know that anything needs to actually change for analog yet.
Great. Okay. Well, you know, Qualcomm is a member. There are a couple of guys from Qualcomm on the working group. So if you want to hook up with them, make sure that they get your concerns voiced, or if you want to join, you're welcome. So and that goes for everybody else too, as we mentioned. You know, if you're an Accellera member company and you want to participate, you're more than welcome to. If you're not an Accellera member company and you want to, let us know. We can help you join Accellera. So
yeah, Jonathan, it'd be great to have you join us.
Yeah, I just haven't seen I hadn't seen anything yet that needed the new standard.
Right. Okay. Well, we're always looking for examples too of things that we can attempt to address. So, all right, getting close to the bottom of the hour here. Unless I see any other questions, I would like to thank you all for.
I have a question, Tom.
Yeah, go ahead.
Hey, turn on the camera, make it more interactive.
Hey, Sumit.
Hey, great presentation. I really enjoyed it. Thanks, Tim. So
you have 2 minutes.
2 minutes, yeah. From the vendor specific, I remember you mentioned about Connect module. Is there any recommendation from Accellera? How do you expect it to be implemented? Because it's going to be vendor specific, right?
We're actually addressing a topic on that right now. So this is our initial proposal. Yeah, Connect modules is something that we have been talking about this past couple of weeks in the committee. So we're looking at putting out a standard Connect module methodology that can be used by all vendors.
Okay, so that would be communicated back to the community, correct?
Yes.
Right. Yeah. And part of what happens frequently in committees like this is if there's one particular vendor that has their own way of doing something that's useful to the general community, they can contribute it to Accellera to become part of the standard, and then the other vendors will be able to do the similar thing. So to the extent that any particular vendor has their own way of doing a certain thing, if it's useful to the standard, usually there's value in contributing that. Otherwise, if it's something the committee feels needs to be done, they'll come up with another way of doing it, and then that company has to change what they do, right? So this happens all the time in standards. So
thanks.
All right, great. All right, it's now 3:30, so we're gonna have to call this. Again, thank you very much for attending. Enjoy the rest of DVCon. Hope to see you guys all on gather.town. And remember tomorrow and Wednesday to vote for the best papers and all that kind of stuff as we go through. And thanks for coming.